Okay, so we've been using objects in JavaScript where we have this key and value, and we know some things about it, right? We know it's got constant lookup time. We know that it's got constant adding time, and we know it's got constant delete time, right? So it's got these three things, and so that's kind of like magic. Like how is that happening? And so how that's happening is actually quite a bit of a story. And I've posted videos in our Slack channel made by a personal hero of mine. He's super talented and brilliant, and his name's Hasib Qureshi. And he walks you through essentially how all of this is happening and then beyond. So really it's optional, but really like mandatory in the sense that you really should watch those videos. Take them one at a time. They're really interesting and really well done. And it's essentially what I'm going to try to go over today in a shorter period of time, but his is going to be better than what I will do today. I'm certain. Okay? Because he's better than me in every capacity. He's the best. Okay, so without further ado, I want to first start talking about, hang on, I took some notes. I want to first start talking about arrays. Okay, I want to talk about an array and what is going on with arrays. Okay, so we've got this idea of an array, and we have our RAM, right? This is random access memory. This is like in the machine level, and we can think of it as all these bits of information, right? So maybe this is at 908 and this is 916. These are like the addresses, and this is 924 and 932 and so on. This is our RAM. And when we store things in arrays, right, we can store them like in these specific sections. So maybe I'm storing the number 5 and the number 8 and 2 and 1. And the way we can look things up is because when we make this array, we have this address associated to it, and we also have the length, right? We have this length property. And so when we have the address and the length, we can just instantly look up what something is at a given index, right? Because we can just do the math. This is the second element at 908, so it's just like the index, we'll say in address times index times 8. This is like for the 8-bit or something. So the 0th thing, or this is plus, sorry. So I0 times 8 is 0. Our address is 0 plus 908. 1 times 8 for the first index is 8, and we go to the next element so we can see the 916. And so we can instantly key into these arrays super fast. Okay, so this is arrays on like the RAM level. Now, that's cool. Where's my thing here? Okay. Okay, so this is our arrays. Now, so we usually in a lot of like lower level programming languages, we have something called static arrays. And you'll see these static arrays exist in these lower level. And what static arrays have is they have a defined size or, capacity. So this array already has, we say when we only want an array of length 4. And it goes and it finds a spot in memory, we'll say, that has like four slots available to it, and that's it. So once the array's full, it's full. Right? But in JavaScript, we have these dynamic arrays where we can just keep pushing and pushing things in. Right? So how does that happen? Well, dynamic arrays are built on static arrays, but the idea is that we actually once this array hits its capacity, what it goes and does is it creates a new array of twice the length of the previous array. And we'll see more of that later, so it resizes. So that's how we can keep having these n operations and lookups still, and pushing into an array is still just n, because all we're doing is, like, if we want to double this, sure, there's elements, and we double its length, and we have to still go through all of these things. But then for every time we add a new element, we get an equal number of free pushes, which we'll talk about more later. So what that ends up giving us is something called amortized, which we'll see more about later. Okay, so this is this idea of arrays and doubling arrays, and I just want you to have that in mind. So there's another data type that we haven't talked about yet, and that's called a set. Okay, now sets are, to tell you more like how they behave, is they behave very similar to the way our objects have behaved up to this point, except for they don't have a value. They just have this key. So a set has to have all unique keys. Okay, so a set must have all unique keys, and then our goals for sets are that we would have O1 insertion, O1 deletion, and O1 retrieval for a constant, right? That's fast, just like our objects. So how can we make a set? Right, so we could make an array, let's say, and put some things in there. So let's say we have a 5 here and a 4 here and a 2 here. And if we just have a regular array behaving as a set, when we try to insert into it, we have to check to see if it's already in here in order to do that. So we have this insert of O of n, right? So it takes n time to check. Same with getting. If we want to get something from our set and see if it's there, again, we're going to have to go and search the whole array, again, just to see if it's even in there. So our get is also O of n. And if we want to delete something, hey, Jimmy, if we want to delete something, we also have to go all the way through it, again, to find just what exactly we're even deleting. So our delete method is also O of n. So that's kind of sucks, right? That's not a great way to build a set. So let's think of a better way. So for now, let's just pretend that we are only going to be dealing with integers. We're not worried about our strings, okay? So when we're dealing with sets, we can think about, well, what about if we knew what the min was? Because if they're all always unique, we could make arrays that cover the whole size. So I could make, I could have the numbers of like 2, 5, and 6. And so I could make an array that has a 2, an empty spot here for 3, empty spot here for 4, and a 5, and a 6. Right, so I can make this array, and I could think of each space as this bucket. And more specifically, I could go off of just their index. So let me just make that cleaner for us. So I'll go 0, 1, 2, 3, 4, 5, 6. Right, so these are our indexes. We'll offset it by 2 because that's our current minimum. And we'll make this array where we'll just keep like a true or false value. So we have a true here, a false here, false here, a true, and a true. So this is a way for us to improve this, right? So now whenever I want to add something, I can just make an array to make sure that all the sizes are fit and transfer things over. But if things are already very large, I might just be able to fit it in. So if I want to add a 3 into this, that's really easy because all I have to do is key right into that and switch that symbol to true. I could easily delete from this. I could say, okay, I want to delete a 6, so I can just key right into my 6 and delete and change that to a false. And I also can check if something's in here really easily, right? Because I can go, oh, okay, I can just, is a 4 in here? I can go directly to the 4's address, and I can look and say, okay, it's not in there. Okay, so now we've got something where we're at our O of 1 for all 3 operations. What kind of sucks about this? Can anybody think of maybe a downside to this implementation?
So the way this array, well, the way this set is being like designed, we're designing it sort of like on the pretense of that we know what the minimum is, we know what a maximum is, and like we have like the 5 as sort of like another key, right?
That's
And
right.
we're using the true false values, the Boolean values to sort of like make everything faster because you're just checking to see if it's true or false, right?
Right, because we
So
can look directly at that index and just see.
I'm trying to think. I thought I had a downside. I was gonna say something like, well, like the 4 isn't actually there, or like the 3 isn't actually there. They're just placeholders. I don't know. Like I think it's good. I don't know.
Okay, so we
think
think it's good. What else we
I
got?
think if the array goes to like 2 to like a 1,000, then only 2 and the 1,000 shows up, but then everything in between is false. That is just making 2 huge set. I think that's like a downside for 1.
Exactly. That's Kong, right? I can't see your face.
Yeah, it's Kong. Yeah.
Yeah, Kong. Exactly, right? So what Kong's saying is, well, what if our keys aren't like that nice little group and we don't know our min and a max? And let's say our min is 0, and we have 2 elements in this array, and our element is, you know, like 2 to the 10, right? Some giant number. Well, that's just an unrealistic amount of space we can even use inside of our computer, right? That's just too big. So we're wasting all of this space. So our current idea of creating this array that's predefined in length, that's set up by the min and max, that kind of has to go out the window because that's no longer going to work for really large differences, and it's just going to waste way too much space. So what do we do? So instead, what about if we move to smaller arrays and we use the modulo operator? Right now, if we remember, the modulo operator gives us back the remainder after division. So I could make an array. Let's say I have an array where it's going to have 4 spaces. So we'll have our 1, 2, 3, 4. And I'm going to take any number that I want to put in here, and I'm gonna like mod it to, I'm gonna mod it by the array length. Okay, and we'll put it in like, we'll pretend that there's like these little buckets here, and they'll hold the numbers. So if there's any duplicate numbers, right? So, okay, so we go back and we'll have our, like our 2 and our 5 and our 8 and our 9, and we'll go, okay, so let's go ahead and put these in. So we go, okay, well, 2 mod 4, that's going to give us our remainder of 2. So 0, 1, 2, 3. So we'll go, so we'll mod by 4. And we go, okay, so 2, that's going to go in here. So we'll store this number 2 inside of our bucket here. And then we'll go, okay, we've got a 5. Well, 5 mod 4, that gives us a 1. So we'll put our 5 in here. Great. We go 8. 8 mod 4, that's going to give us our 0. So we'll put our 8 in here. And we go 9 mod 4. That's going to give us 1 as well. So we'll also be putting our 9 in here. Okay, so this you might think, okay, well, this is kind of working, right? And assuming that the numbers are random, there's a pretty good chance that we're going to have a nice even spread here. Now, what about though if we have something called like pathological input, which means the user's not putting in well, actually, let's get to that in a minute. I'm going to go back to that. But essentially what I'm saying here is we've got this, but if we keep filling this up, we eventually, this is not going to help us anymore because we still, so if somebody says, hey, does this number exist? We can go, oh, okay, great. So does 5 exist? And we go, okay, well, 5 mod 4 is 1. And then we have this bucket, and we got to look through this bucket. Now, in the worst case scenario, all of our numbers could end up in this bucket, right? And then, so in that case, our worst case is back to being O of n, right? So that's not going to quite work. So instead, what we want to do is start thinking about, well, maybe we could do resizing. So as this fills up, we can resize this array and transfer everything over. Okay, so what do I mean by that? Okay, so let's say we have 4 buckets, so we can hold 4 things in these buckets. Okay, but now we want to add, let's say I also want to add a 7. Right, so now that's not a very good 7. Now I want to add a 7. So I have to resize. Now I'm going to, because of like time constraints and whatnot, I want to just jump. So the best way for us to resize is to actually double the array length. And I can prove that for you in a minute. But for now, let's just go ahead and double the length. So we'll make our new array. So we'll have our 0, 1, 2, 3. And we'll also have our 4, 5, 6, and 7. Let's see, can people still see that? No, okay. So we've doubled the length. And so these all still have their buckets. Okay, and we have to remod all these. So that's a negative, but we have to do it because if we don't, well, when we did this before, so like 8 mod 4, well, that gave us 0. Hang on, I can do 1, I'm sure. Okay, 5 mod by 4 gave us 1. So if I could put the 5, if I can't just transfer the 5 in here. I actually have to remod it because now we need to be modding by 8. And so 5 mod 8 actually gives us back 5. So the reason that's important is because if I just transfer everything over and then the user says, well, hey, does my 5 exist? I'm going to go, okay, 5 mod 8. I'm not going to know that I put the 5 in when our array was originally a 4. Okay, so I have to remod everything. So let's go through that. So 2 mod 8 gives us back our 2. So I'm going to put the 2 in here. 2 here. 5 mod 8, that gives us 5. It's less than 8. 8 mod 8 gives us 0. So that's our 8 here. 9 mod 8, that gives us 1, 9. And our 7 mod 8 gives us 7. And we have our 7 here. Okay, so now we've got this nice distribution along our buckets again. So on average, if we have this n size of buckets increasing with our n inputs, we will get around 1, or and actually if you work it out, it's actually less an average of less than 1 element per bucket, which is good.
right.
That allows us to
Let me
look
stay
at and get it up at constant time. Deja or someone, I hear you. Mute. Okay. Questions on this so far?
So the placement of like the numbers like in the buckets, like all of that depends entirely on the length, right? It depends entirely on the length, because that's what we're modding by. And
right.
so that's how all of that's being spread out. So the reason why you couldn't directly transfer the elements in the same position as they were in the first array was because like it normally would it will double that array size because we need to fit more things in there. So now it's like we have to be sure that they're in. We have to put them in the new places, and then like that's now where those elements exist. We can't say that the element of 5 exists in 1 anymore because it doesn't in this extended array.
That's exactly right. Yeah.
Okay.
So we have to remod everything when we go through it. Now, believe it or not, this is actually O of 1 per push. And I can show you why. Okay. So let me just erase some of this and start going, and we'll say like, okay, so let's say we start with an array of 4, right? So just gonna make this line here, and we have our 1. This will be my y-axis. Just going up, we'll say 1. I'd like to make this more dramatic. Okay, it doesn't matter. 2, 3, 4. Okay, so our first array would fill with 4 things. It takes this. Now we have to go up to 8. So this is gonna be, we're going to have to do this long thing. We're going to have to create all these extra squares, spaces. And we have to iterate all through these 4. But we'll have 8 now. So we'll have 1, 2, 3, 4, 5, 6, 7, 8. We'll have to insert all these. Then it will go up to 16 once we fill up that 8. So now we should have another 16, 2, 3, 4, 5, and so on all the way. Now, this isn't the greatest graph as I was hoping for, but what you'll see is we're paying all this up at cost up front in order to make room for all these other items. So if you were to actually make these fall and lean down, so if you were able to collapse these towers, because you've already paid this price, and you collapse this tower, so it goes there and there. After they've all collapsed down, you'll see that the way the math actually works is that by doing this amortized thing where you keep doubling the number with every time you meet capacity, your price of insertion becomes O of 1, becomes constant because of something called amortized. It's an amortized cost. It's not the exact same thing as an average, although this is the average case, but it is amortized is essentially means that you will be paying all of this up front and that it will even out as you split it up. So it's used in like insurance, I think, a lot and stuff, because you have like your amortized costs of things. Yeah, amortized loans. So you're getting it all up front and then paying. So this is an important concept for how we're keeping things O of 1 on insert, even though we have to keep going through it and remodding.
Corey?
Yes.
In the first diagram that you drew, when we had the array with just 4 empty items in the array, 4 buckets, right? One of the buckets you had 2 numbers and you had an empty bucket, but to add another number, you had to double it. To add that 1 extra element, why did you double it when you could have just put it in that last array?
Right. Great question. So we have to think of these arrays as having a capacity. So it was already at capacity, even though it was still in that bucket, we did reach that capacity. And so in order to make it, because ideally we want one or less items per bucket. Because
Ideally, you want one or less items.
that's right. Right.
Okay.
Ideally, we want one or less items so that it's instant to look through it. We don't want to look through a bunch of items.
Right.
So just because there's a bucket open doesn't mean we shouldn't keep going, because we don't want a bunch of items in that individual bucket anyway.
Okay. So when just by adding that one extra element, you double the size of the array. Isn't that a lot of memory going just for one extra element?
Good question. Yes. I mean, you're doubling the size of the array. Is that a lot of extra memory? It depends, but it's scaling with n. So the expectation is that you'll continue to be using that memory.
Okay.
If you were only ever going to put 5 items in, then you should have started with like a smaller array instead of trying to build like this idea of dynamically including it. But since we don't know how the size of the array already, we got to scale it with our n. And in order to keep that rule of constant time with amortization, we need to double the size of the array. So we get that many free pushes per n size of increase.
Gotcha. Okay.
Okay. So this brings me to the next point, which is when we were dealing with those buckets, right? Somebody could put what's called a pathological input and control what goes in there, right? They could put 2, 4, 8, 16, 32, right? And if we had buckets, even with doubling it, we'll end up getting a lot of duplicates in the mod because these are all 2s, right? These are all based around the number 2. And we also have a limitation right now of only working with integers, right? So this brings me to the next point, which we are going to talk about, which is hashing. Okay, so hashing you can think of, and if you watch those videos that I posted, they will be better than this, although they will take up more time. Hashing you can think of as this function that takes things in one way, takes things in this way, and put things out that way. It is a one direction function, right? And what hashing does is it derives some kind of, well, as Haseeb puts it, garbage, right? It's some random looking string of garbage. You know, it could be like some 32-bit thing where it's like some like, you know, I could put in a 5 here and I get back some like 7, 8, 1, 9, 2, 1, 6, 4, whatever. Doesn't really matter. The thing is we have no, and so the thing that makes a good hashing function, and it works with strings, it works with numbers, it works with anything. Okay, and what makes a hashing function good is it's deterministic. So let's write that. Let's deterministic. What is deterministic? Deterministic means something happens for every time. It never changes. So every time a 5 gets put in, this random looking number comes out. Every time. If I put a 7 in, some other random looking thing comes out. Okay? It's uniform. This is also makes a good hashing function.
Yeah, no matter what comes in, that random's coming out.
Some random thing is coming out, but whenever that thing comes in again, it will always put out the exact same thing. Okay?
Yeah.
Very, that's like very important. It must always produce the exact same thing. One thing must always produce the other thing. So every time I put a 5 in, I need to get this number back. Always, have to. If not, it's not a good, it doesn't work. Everything breaks. Okay? So that's what our deterministic means. The same thing happens every time. It never changes. You could put it, I could put a 5 in tomorrow. I could put a 5 in a year. I'm always going to get back this kind of random garbage. Always. Now, it's also uniform. A good hashing function has to be uniform. Uniform means that each output is equally as likely. Okay, so each output equally likely. Okay, so we have no, because of that, we have no idea what the output will be. We cannot predict, given something to put into our hashing function, we have no ability to predict what's going to come out because every possible outcome is equally likely. Okay, so it's super deterministic. So every time we put something in, it puts out the exact same thing, but we have no ability to guess because every single thing is equally as likely. So we have no idea what it will put out unless we actually put it in. Now, it also has to be one way. One way or highly sensitive. So that means given output, there is no way to predict the input. So if I see this, I have no way of knowing that this came from the 5 if I'm only given this, right? And everything and because it's so highly sensitive, you know, let's say I put two words close together. Let's say I put beard and bread, right? These words are nearly identical, same letters, just a couple mixes, right? These outputs should be totally unrelated, right? They should have nothing to do with each other. You should not be able to be like, oh, because this number it made this and this, I can kind of guess what's going to happen. You should not be able to guess what's going to happen.
Right.
This is a true hashing function.
So Corey, like stuff like passwords can probably be useful for this type of stuff, right? Like
absolutely. I'm glad you mentioned that. So passwords do get hashed.
Awesome.
All the time. And sometimes you get hashed. A password can get hashed multiple times even before it gets added. So it's hard to know how many times it's even been hashed.
Nice. Okay.
And then certain hashing things also have things called salting, where they salt the password and they add all of this other stuff into the hash to make it just that much harder to decode. So you should never store someone's password in your database, but you can store, you know, someone's hash version of that password because it's always going to put in the same thing. It's going to be deterministic. It's going to be highly sensitive. And if someone gets a hold of that and cracks into it, they'll have no ability to know what was originally entered before.
Right. They'll literally only have access to the hash. Okay.
That's right.
My bank does something like that. Like if you use your debit card to purchase stuff at Amazon or something, instead of when you put your card number, it creates random numbers and stuff that's not equal to that card number. Only you would know that, and so hackers can't go and steal your card information.
Yeah.
I think it's the same concept, right? Or no?
Yep. Yeah, that sounds right. This is very important for ideas of security, but we're going to use this as well for the next thing. So there are different kinds of hash functions. People can make their whole careers, I think, like building out hash functions. Like it is really hard to build a true hash function, right? That's not just like an easy task, but there are ones that exist. Some of them they're standard and faster. One of those can be called, one of them is called city hash, CRC, RC32. This is maybe something you've seen or you haven't seen if you've used BitTorrent and stuff. They use a CRC32.
Yeah.
It's basically checking to see if the information is correct. There's a murmur hash. Murmur hash. This is what Ruby uses built in. That's kind of fun. Ruby does a lot of hashing under the hood. And then there's also cryptographic hashes. So this is like standard and fast. And then you have cryptographic. Cryptographic. And those are generally slower, but have fewer collisions. So these are slower and fewer collisions. And I will explain what a collision is in a second. And what else is there important to know? Examples of some of these, there used to be one called MD5. That's no longer used. Other examples of this is SHA-2, I think it's called. SHA-2 and Blowfish was one at a time. And you know, people are always working to try to crack and solve these. And so once they have, some of them are no longer used anymore because they've been cracked, and we have to make a more secure hashing function. So cryptographic hashing functions are a bit slower, but they have fewer collisions. So what's a collision? Well, you know, a hashing function isn't perfect. So a collision is when two things get the same output. Two things get the same output. So this is possible, right? Eventually, there can be collisions. The better the hashing function, the more secure, all that, the fewer collisions. But that doesn't mean there aren't ever any collisions. Collisions are still possible, okay? So let's keep going. So the next thing to be aware of is linked lists. And we have talked about linked lists before in this class. Linked lists are made up of a node, right? Of nodes. They usually have a head and a tail, and they have a pointer to their next. So they have a next property, and they have a value, you know, right? A value. They have a value and next. This one points to null. Let me write next here too. Sorry. Okay, so we've got these next properties in our linked list. And we also can have a previous property if we want to make a doubly linked list. So we can add this prev and point to this way, and we have a prev. We point to this way, prev, and point to this way. So a doubly linked list is really nice because you only need the node itself to delete itself, right? Because you can kind of make it circumvent. You can look at, if I want to delete this node, I look at who its next node is, and I assign its previous to be my current node's previous. And then if I have to look at its previous, which is here, and I assign its next node to be what that node's original next node was. So now these nodes can point to each other and just circumvent this node, and it will get garbage collected in the memory because nobody's referring to this node. This node no longer matters. Okay, so, and when you create your linked lists, your doubly linked lists, it's good practice to have sentinel nodes, sentinel nodes. And what a sentinel node is just to have, when you create your doubly linked list, is to have this head and this tail. that start off just pointing to each other, but they don't have a value. And this allows you, when you're writing your code, it keeps things a little bit cleaner because you don't constantly have to check like if there's a head or there's not a head. You can just go ahead and grab from this head and assign like, oh, I'm adding this. This heads.next is now this node, and what its previous next is now its previous, and it's just some reassignment. Okay. Questions on what a doubly linked list is? No. Okay. So this brings us, once we've got this idea, we start to get really close. So we can combine these things, right? So when we actually, now, we want to start thinking about our hash map, right? So we've got hashing now, and we've got this array, this ability to keep storing information and have these n lookup, constant lookup times with that array that keeps doubling in size. And so now we can put it all together, because now we have this ability to create these random numbers with our hash. So we start off and we can have our array here, and we can have our 4 buckets, right? And so I can put in my 5, let's say 5, 4, 9, and 6. Now, you may have been thinking of these buckets before as arrays, and that's okay. But there's reasons for linked lists to be actually better in these scenarios, but we won't get to that today. So, but they are in those videos if you watch those videos. So we got our hash, right? And so we've got our mod. We're going to be modding things by 4. And so we put our 5 in, and we get some, and here, well, just 1, 2, 3. And so when we put our 5 in, we no longer are modding 4 to 5, but we put our 5 through our hash, right? So we call hash on our 5, some random hash function. And so we get back some really weird number, and we don't know where it goes, but we mod that weird number by 4, and so we can go ahead and put that in that bucket. Because every time we hash 5, always, we're going to get that same random number, and we'll know we can get it there, right? That's the same with a string, right? So how does this actually relate to our key value, right? And we can do the same with our 4, hash 9, and it all is going to fill up. So let's say we want to make our object now. Okay, and so in our object, we want to have 3 point to 2, we want to have 6 point to 8, we want to have, let's say 1 point to 7, right? And so the way this works in our programming is we know that the keys have to be unique, right? That's one of our rules for our objects. So we don't want to hash the values, because the values don't have to be unique. But when we hash the keys, so we can hash this 3, and we get back some random number, we multiply 4, and then we can store that 3 in here. We can store, well, we can store this node. Let's call each one of these buckets actually a doubly linked list. Okay, so we actually point this, we'll go downwards to this node, and this node will have a key property of 3 and a value property of 2. But we know to put it in here, in this spot, because of the hashing and the modding. Okay, so then we get to our next thing, we say, okay, we want to have a 6 pointing to an 8. So we put the 6, our unique key, into the hash, and we get back some specific weird number, which we mod by our 4 here, and we go, okay, let's go find where that bucket is. So let's say it brings us to our 1, or I'll say our 3 because this is kind of in the way. I can move it. Mod 4, just to remember what we're at. Okay, so we say, okay, well, I have 6, 2. This is going to be here. And so we have to check this linked list like, hey, is our 6 already in here? Because if it is, we want to reassign it. Otherwise, we're going to add this new node here where we have our key is our 6 and our value is our 8. And this can keep happening. So we add our 1, 7. It gives us a random hash. We mod by 4 and from the key. And maybe it goes here. Maybe there is like a collision in the box, but that's okay. And so we'll go here and we'll add our new node here where we have a key of 1 and a value of 7. And that's a doubly linked list. And that is actually how a hash map is implemented. This is how it's actually happening. Now, you may say to me, I don't get the point of the doubly linked list. Why don't I just have things in here where I make tuples? So that's what you call an array with 2 elements in it, like a bunch of them. They're called tuples, right? Why not just put my 3 here pointing to a 2 and my 1 here pointing to a 7 and my 6 here pointing to an 8. Why can't I just have my buckets be arrays filled with tuples? That's a great question. So for the basic implementation of a hash map like this, that is totally fine. Totally fine. You could make this work the same. So we currently have, let's just go over it one more time. We have our insertion. Our insertion takes O of 1 because we'll take a key, we'll hash it, we'll mod it, right? These are all math, just constants. And then we can go ahead and check that bucket and go through it. And we are guaranteed because of the hashing function's randomness that they won't all be in that one bucket. And we're going to keep amortizing. So on our insertion, we can say it's going to be constant. For getting, it's the same thing. We're going to hash get. We'll check to see if that key is there in that specified bucket. So our get, we'll say, is also O of 1. And to delete, it's really easy as well. We can just go and delete ourselves, our node, once we've, again, hashed the key, gone to the bucket after modding, and found ourselves in that list, which is probably 1 or less. Okay, so we'll go ahead and say our delete is also O of 1. Okay, now the tuples are fine if you wanted to do that, because there really won't be a lot of elements or items in this bucket. Now but I will say that it's the classic and better practice is to make these buckets doubly linked lists. That will become way more important when you move into something called LRU cache. That means least recently used. And the goal is not to go into that today, but when you do try to start implementing something like that, you will find that you will need to have a doubly linked list in order to make it still all work within our given time complexities. So the tuples really won't work for the data structures that you can set up outside of the hash map. But for just building a hash map, tuples actually will work. But ideally, you would be using linked lists as your bucket. Okay, that is everything. Whew, I know that was a lot. I really encourage you to not necessarily rewatch this video, but to actually go back and rewatch Hasib Qureshi's video. It's going to be slower paced, a little bit more time on each thing, better whiteboarding experience, and overall, just, I think, a better lecture. But hopefully this gives you a little bit of a primer for that lecture and a little bit of a taste. Any questions on any of this stuff?
So like the reason why I'm thinking that linked lists would probably be better anyway is because like the amount of data we're going to be storing and like dealing with like, you know, like it'll probably be easier to access all of that information in those individual buckets if we can just look at whatever address it's pointing to and just go get it. So
Well, exactly. The address is going to be what becomes very important when we start doing the LRU cache.
yeah.
Because the LRU cache, we have to keep track of the least recently used thing. So if a new thing comes in, we have to go ahead and get rid of that least recently used.
Yeah.
So the indices would have to constantly be changing, and we wouldn't know. Well, if we have a doubly linked list, we can have the lists all point to each other. So when it's time to delete one, it's very easy, and the new one can just go ahead and be appended to the head.
So it's like no matter how much new data is coming in or how much crazy things like change around, it has access to an address, and that address is going to point to that data that you need anyway. So
Absolutely.
Okay, I think I'm starting to follow along. It is like, you know, it's new stuff, you know, still, so it's a bit like kind of crazy still, but I'm gonna watch that video because like
watch those videos. Oh my God, I'm telling you, they are better than Titanic. They're better than Shawshank Redemption. They are top notch. Sling Blade, fuck Sling Blade. This is so good.
Sling Blade 2. This is what this is.
I reckon this is a real good. Any other questions on what the heck's going on? How do we make a hash map?
Wait, I have a quick question. You said that you hash the keys in the object, and then you mod that random number.
Yes, I'm modding that number by the length of that array that we're using.
Mm-hmm. So then, if you mod that random number, how does it like what index are you putting it in that case? Since it's not by like the remainder, you know, the modulo remainder.
That's right. It's
so you still get that with that random. Oh, okay.
So that random number, we're still going to be able to mod it, you can say, and get back that remainder, which is always going to be the size less than our array down to 0, right? It can only go from 0 up to n-1 for the length of an array.
Okay.
Great question. What else? Any other questions? Okay. Temp check. How we doing? Temp check, temp check. Okay. All right, a couple more people maybe. Left, 3, 2, 1. All right, cool. This is where we are as a class. Not a bad place to be. In the 3s. 4s, couple 1s and 2s, total of 5 people. Definitely follow up, watch those videos, ask the questions on what's going on. Everybody else, also like just go ahead and read, watch those videos. They really will help. He does a phenomenal job explaining it. That being said, this is also really important stuff to know. This is very good to know, especially for the interview and also for building out your own LRU cache and all that. That's all going to become, that's a valuable skill set to have for interviews and to really understand how things work, right? Just makes you seem more of a pro the more things you know how things work. Besides that, there are some hash questions, I believe. Yep. So if you just allow me to share my screen for a second. in our pursuit core DSA, same area that we were yesterday. There are a couple questions, 5 questions today about hash tables. None of these actually are about, I don't think, the theory of hash tables and how they actually work. This is more just using objects to be advantageous in your problem solving. Highly recommend, we're going to work on these for the rest of the day. Highly recommend to put a focus on two-sum. Two-sum is one of the most famous ones. And I think you may see that one again even before your interview days. So I would definitely put an extra focus on two-sum. But go ahead and work on all of these. And that's the end of the day. Okay, so I will be around to answer questions, to help out, but everybody